So far in chapter 16, we talked about this Loren series and residue integration. And we introduced the Loren theorem or Loren series. One part is with positive powers of Z minus Z naught expanded around Z naught. These are positive powers of Z minus Z naught, and we have negative powers of Z minus Z naught. This part is the Taylor series. This part is the principal part that has, singularity at Z equal to Z naught. And the coefficients an and bn are given by these formulas. And of course, you can write them as one thing right down here. But the main point to highlight here is when n is equal to 1 for bn, then we have Z minus Z naught to the power 0. So this goes away. And then we have integral over closed path of closed simple path C of fz dz. And that enables us to evaluate that integral if we have the Loren expansion or Loren series, to write that integral of fz dz equal to 2 pi I times b1 when n is equal to 1. So it means that with all these n and infinitely many terms that we have, only one of the coefficients is important, which is b1. And that is called the residue of f of z at z equal to z naught. And we can write the integral of fz dz only in terms of that residue, 2 pi I times b1. That, of course, is when the z naught, which is the center of expansion of the series, is inside this closed path. All right. So this is basically residue theorem, and we categorize the singularity, singular point at Z naught, based on how many terms do we have in this principal part. If we have infinite number of terms, means that this goes to infinity. It is in fact n from 1 to infinity, then we have essential singularity. But if it is finite, we call the singularity a pole. We call it a pole, and we say m, which is the highest number here, the highest power in the denominator, if you wish, is called the order of that pole. If that higher order is only 1, means we have only one of them in this series, the first one, we call it the simple pole. Okay, and that b1 is the factor of that simple pole. This was an example when you want to integrate this sine z over z to the fourth. You can write the Loren expansion, which becomes the Taylor series for sine of z. And then if you divide by z to the fourth, you get these terms: 1 over z cubed minus 1 over 3 factorial z, plus this has constant, this is a constant term, 120, 1 over 120, and this is z cubed and so forth. So the next terms are all positive powers. And you see that this is like at z naught equal to 0, because z minus z naught is just z here. And then we look at the coefficient of 1 over z minus z naught, or 1 over z in this case. And that coefficient is negative 1 over 3 factorial. And only that one is important for this integral. And therefore, we write that integral equal to 2 pi I times that factor. That factor is negative 1 over 6. So we write 2 pi I times negative 1 over 6. So it becomes negative pi I over 3. So this gives us a very fast, powerful means of integration. All right. And then we said that because only this b1 is important, the factor in front of 1 over z minus z naught, we don't need to write all the Loren series because we just want one coefficient. And therefore, we can have formulas for that one coefficient. Here, if the pole is a simple pole, means that m is equal to 1. If it is a simple pole, then B1 will be the limit of z minus z naught times f of z as z goes to z naught. So by multiplying this z minus z naught by f of z, we actually cancel that denominator and then evaluate that expression at z minus z naught. I explained how this becomes B1 because all the terms now have a factor of z minus z naught. If you put z equal to z naught, all those other terms become 0. The only term that remains here will be B1. And then we said that if you can write f of z in terms of a polynomial or even a analytic function divided by a polynomial, another polynomial, then the residue of the f of z at z equals to z naught becomes this one analytic function evaluated as z naught divided by the derivative of the denominator evaluated as z naught. I also showed why this is equivalent to this one. All right. And this was an example that I'm not sure if we did that. We said that if you want to find the integral of this one around z equal to, let's say, I, this has a simple pole at I because you can write the denominator as z times z squared plus z plus 1. And then z squared plus 1 is z plus I times z minus I. Then you can find the residue this way. Residue of this whole function at z equal to I will be, there are two ways to do that. We have two equations, two formulas. One is this. You multiply the function by z minus z naught, which is in this case I, and then evaluate the result at z equal to z naught, which is I here. So you multiply this whole thing by z minus I, and then you write that also factor the denominator becomes z times z plus I times z minus I, and you see that z minus I cancels, and then you get 9z plus I divided by z times z plus I, which is like this, evaluated at I. So if you put I here for z, you get 9z plus 9I plus I, which becomes 10I. The denominator becomes I times 2I. I times I becomes -1, so it becomes -2. So it becomes 10I divided by -2, which you can simplify, becomes -5I. All right. Or you can use the second formula. This was the second formula. Residue will be, if you can write like two polynomials for that, you just take the derivative of the denominator, not the derivative of the whole thing, remember. The derivative of denominator and then evaluate at z naught. So this will be P in this case will be 9z plus I, and then P at I becomes 9I plus I. And Q prime of z means the denominator, derivative of denominator becomes 3z squared plus 1, right? And the residue, therefore, will be residue of this will be 9z plus I divided by 3z squared plus 1, evaluated at z equal to I. And if you do that, again, get 10I in the numerator, the denominator becomes 3 times I squared, which is -1. So -3 plus 1, again, becomes 10I over -2, which becomes -5I, the same as here. See, they both give you the same thing. Any questions so far? All right. Now, what if we have poles of any order at z naught? Means this was these two formulas were for simple form. When the highest power in the denominator for z minus z naught is 1. But what if we have higher power in the denominator? So we have this formula for the residue of f of z at an mth order pole at z equal to z naught. This is the formula. It seems like a complicated formula. What this says is that you multiply this f of z by z minus z naught to the power m, and then take m minus first derivative of that expression. And then take that limit of that as that goes to z naught, and then divide the result by 1 over m minus 1 factorial. I want to show you briefly where this comes about, where this comes from. Do you guys see where it comes from? It's not very obvious, but if you write f of z, let's say you have f of z as a Loren series. You have a Taylor series, an z minus z naught to the power n, goes from 0 to infinity. This is the Taylor series part, which is the analytic part, plus the other factors. Let's separate. I can write sum of bn over z minus z naught to the power n, as n goes to from 1 to infinity. So I want to separate b1 over z minus z naught to see how we can get b1, plus the other terms, sum of course, it is the mth order, sum of bk over z minus z naught to the power k. K goes from 2 to m because we have mth order. So f of z can be written as this. Now, if I multiply this f of z by z minus z naught to the power m, what do I get? So f of, let me write first, z minus z naught to the power m times f of z. What I get here becomes the sum of an z minus z naught to the power n plus m, right? And then n goes from 0 to infinity. This is the Taylor part. Plus, we have here z minus z naught to the power m minus 1, because we have negative 1 here, times b1. And then the other side become, the other terms become sum of k from 2 to m bk divided by z minus z naught to the power k minus m, right? It cancels a power m. So I can write this in the numerator, right? I can write m minus k in the numerator. All right. So the point is that this has k minus m. M is the highest one. Now these are all negative power. I think it's better to write in the numerator because now they're all negative, positive powers. So I can write bk times z minus z naught to the power m minus k, right? Now here m is the biggest one, so the last one for k is k equal to m becomes 0, and we have bm is one number. The one before that becomes bm minus 1 times z minus z naught, and then we have all the powers until we get to m minus 1. All right. So the first one starting here is at k equal to 2, so become m minus 2. So now this is this expression now. What happens if we take m minus first derivative? So this basically, if I write it down, it becomes b2 times z minus z naught to the power 2 plus b3 z minus z naught to the power 3 and so forth, right? And yeah. So it goes until bm, right? When k is equal to m, then you have bm z minus z naught to power m minus m. So you get bm only without any powers. All right, now what happens if I take m minus first derivative? The first derivative, this goes away, the next one becomes a constant. And this power becomes m minus 2. In this power becomes m minus 2. The second derivative, then the last one again goes away, and the next one becomes just this number. And if you take m minus 1 derivative, all of these go away because actually, you know, this becomes m minus 2, m minus 3. I made a mistake. All right. So if you take m minus 1 derivative, all of these go away. So all of these go away, and all of these become, if you take n minus, they all have some power of z minus z naught, because if you take m minus 1 of these power, it starts with n plus 1, and n goes from 0 to infinity. So all of them have still z minus z naught to some power. All right. And when you put z equal to z naught, these go away. So, and these are also go away. What remains is this. But what does remain? When you take m minus first factorial, this goes away. Sorry, m minus first derivative, this goes away, but the power comes down. So you have m minus 1 factorial here. That's why we divide by m minus 1 factorial to get b1. You see, all of these is a trick to just get the b1. All right. And it shows here, as I show, all of these go away with this trick. And the only thing that remains is b1. So that's why we have this formula for the residue. So this is, in fact, b1. Okay. So we don't usually have this m very large. We usually have m equal to 2 or 3 maybe. So what if we have m equal to 2? If we have m equal to 2, means m equal to 2 means m minus 1 is equal to 1. So we have only one derivative, and z minus z naught to the power 2 multiplied by f of z, and then m minus 1 factorial, which is 1 factorial, becomes 1. So this goes away, and this becomes just 1 factorial. So for that residue at z equal to z naught, when m is equal to 2, becomes limit as z goes to z naught, and time limit of z minus z naught squared f of z, then first derivative. So it means that you multiply f of z by z minus z naught squared and take one derivative, and then take the limit as z goes to z naught. Okay, so this is the case when m is equal to 2. So for m equal to 2, we have this. All right, z minus z naught squared times f of z prime, which means one derivative, and then evaluate as z naught. And what if m is equal to 3? If m is equal to 3, then you have this third power and second derivative, and you have 3 minus 1 factorial here, so it becomes 1/2. So for m is equal to 3, the pole of the third order, a residue of f of z, z equal to z naught, equal to 1/2 of limit as z goes to z naught of z minus z naught cube times f of z second derivative, right? So the formula becomes a lot easier to look at. I mean, this is a lot to look at. And at the most we have is m equal to 3. I haven't seen an example with n equal to more than 3. Okay, but it could be. All right, so this is an example. Let's say we have this function. We want to find the residue of that at some point that has singularity. So you can factor this denominator as z plus 4 times z minus 1 squared. And it has a pole at 1 and has a pole at -4, right? But the pole at -4 is simple pole because we have power 1 here. But the pole at 1 is a second order pole. So if you want to find the residue as z equal to 1, we can multiply by z minus 1 squared, and then take one derivative, and then evaluate at z equal to 1. All right, so if you do that, you get derivative of 50z divided by z plus 4. See, z minus 1 squared cancels. You have derivative of that at z equal to 1. So if derivative of that becomes derivative of numerator times the denominator, so limit at z equal to 1 of 50 times z plus 4 minus derivative of denominator, which is 1 times numerator 50z divided by denominator square z plus 4 square. Now this 50z and this 50z cancels, so it becomes 200, 50 times 4 over z plus 4 squared evaluated at z equal to 1. So if you put z equal to 1, you get 200 divided by 5 squared, or 25. 200 divided by 25 becomes 8. Right? So you multiply by z minus 1, z minus z naught squared, take one derivative, and then evaluate at z naught. That makes sense? All right, any questions?
So when m is equal to 2, we take the first derivative,
yes,
and m equal 3 is the second derivative, right?
That's right. You see, sorry. Here, as we have m minus first derivative. So if m is equal to 2, we have only one derivative, right? If m is equal to 3, we have two derivatives, one less than the order. Okay. So
okay, thank you.
You're welcome. All right. What happens if we have several singularities inside the contour? So far, we talked about one singularity inside the contour. This is the more general residue theorem that goes like this. Residue integration can be extended from the case of a single singularity to the case of several singularities within the contour C. This is the purpose of this residue theorem. The extension is surprisingly simple. Here's the thing. Assume f of zb is analytic inside a simple closed path C and on C, except for finitely many singular points z1 to zk inside C. Then the integral of fz taken counterclockwise around C equals to 2 pi I times the sum of the residues of fz at all the singular points. So where does this come from? I want to give you a little bit of insight, kind of a proof to where this comes from. So this is the situation. You see, we have singular points, Z1, Z2, Z3. Let's say there are 3 of them. And then we have this simple closed path that includes all these 3. Okay. So for each one of these 3, we have a neighborhood around it where it is that circle is inside C. So when we go around C, we can deform this contour, like stop here, go to this circle, go back, go around this way, and then come back here. All right, and then go here, go to this circle, go around this, and come back. And then go to this one, go around, and come back. All right, and notice that when I'm going around these, I go clockwise. On C, I'm going counterclockwise, but when around these circles will be clockwise. All right, so now going back here. Now look at this whole thing. It is this whole path that I drew here. That's a simple closed path, right? Because it doesn't intersect itself. And there's no singularity inside that. Do you see that? That's the inside this path, right? There's no singularity here. Do you see that? So what does the Cauchy theorem says? Cauchy theorem says that if you don't have any singularity inside and on the curve, then we say integral. Let me call this whole thing C prime. That I deformed. In fact, I deformed C, and I went over those circles. Integral over C prime, this closed path of f of z dz is what? What do you think it is? There's no singularities inside the path, right? Yeah, it is 0 because the function f of z is analytic everywhere inside that closed path C prime and on the C prime. Okay, so this is 0. Okay, because you see, with this trick, I put all of these Z1, Z2, Z3s where singularities are. I put it outside that that path, right? It is they are outside the path. And then now, if I write this this integral split it into pieces. One part is around C, right? One part is around this, let's call it C1 and C2 and C3. And in here, when we go here and come back, because the function is analytic, going this way and then coming back, and when these distances approach 0, these tend to be the same because the function is analytic and it gives you 0, right? In here, going to the circle and coming back, they cancel each other along those straight paths. Okay, so those cancel each other. So we can write this integral over C prime equal to integral over C of fz dz plus integral over C1. Actually, we're going counterclockwise, so must maybe call it negative C1 fz dz integral over negative C2 fz dz integral over C negative C3 fz dz and equal to 0, right? And now we know for these C1, C2, C3 that if you go counterclockwise, now we're going clockwise, but that's why I put negative here. If you go counterclockwise, the integral becomes 2 pi I times the residue at the singularity, right? So this part becomes 2 pi I times residue at Z1. Is it equal to Z0? Z1, right? This one becomes 2 pi I, sorry, with negative sign because we're going clockwise. This becomes 2 pi I times residue of fx of fz at z equal to z2. This one becomes negative again, negative 2 pi I residue of f of z at z equal to z3. All right. And then if you move all of these to the other side, this becomes positive, positive, positive. So then we have integral of fz dz equal to integral around c fz dz equal to 2 pi I times sum of all those three residues at z1, z2, z3. Sum of the residue of fz at z equal to zj. J goes from 1 to 3. And in general, if there are k of them, we do the same thing, goes to from 1 to k, right? And because these are isolated singularities, for each one we can create a neighborhood that doesn't include any other one, and this process works. All right. So this is residue theorem, and this shows kind of a proof that and insight on where they come from. All right. Of course, I could say for the first one too. But anyway, that doesn't change anything. All right. Does it make sense? Any questions? All right. So this is the proof of residue theorem. Now let's try that. I want to ask you this. What is the integral of 4 minus 3z divided by z squared minus z dz counterclockwise around the simple path shown, that ellipse that you see? I want you to think about it and answer A, B, C, D, or F. All right, be careful, take your time and answer carefully. Let me end it now and share the result. All right. You see, the most popular answer was A, and second was B. So does anybody want to share their thoughts on that?
I think we have the point z equal 1 inside of the circle.
So what was your answer?
It's a 2 pi I.
All right. Is the z equal to 1 inside the
Oh, my bad. Yeah. So it should be here.
Yeah, you see the singular points are outside the path. So means that the function is analytic everywhere in here, in this region. So when it is analytic, then the function is analytic, the integral is 0, okay? It is only non-zero if there is some singular points inside, okay? Again, Cauchy's theorem applies. See, we have a region or domain over which the function is analytic. Let's say this is the domain over which, in which the function is analytic, and we have a simple closed path inside that domain. And because the function is analytic everywhere in that domain and inside the path, then Cauchy's integral theorem still works. The integral is 0. Sorry. So the answer is 0 because the integrand is analytic on and inside the path. All right. So that was a trick question. Don't fall for that. First, we said that we see all these residue theorem was for Z1 to ZK inside C. If they are outside, doesn't affect the integral. All right. So that was the key point here. It should be inside. All right. So this is that. And now, what about this path? So I think you can answer that now quickly.
This one, 2 pi I for sure.
Yeah, all right. So in order to answer that, let me just write myself. I think most of you get it now. We have to calculate the residue as z equal to 1. So residue of f of z at z equal to 1 becomes the residue becomes limit of z minus 1 times f of z, which is 4 minus 3z, divided by z times z minus 1 at z as z goes to 1. So that z minus 1 cancels, so becomes 4 minus 3z divided by z evaluated at z equal to 1. That becomes 4 minus 3 divided by 1 becomes 1, and the integral of fz dz around that contour C counterclockwise is equal to 2 pi I times the residue, this is B1, times B1, which is 1, so it becomes 2 pi I. So that's the answer. All right. So it becomes like that. So the answer is 2 pi I. What about if we have this one? Let me ask you that now. What if we have this path? I give you the poll again. You answered that.
Let me try. Like,
yeah,
the z equals 0 inside of the circle, so we calculate the residue at z equals 0.
yeah.
4 minus 3 times 0 over 0 minus 1, which is negative 4. Multiplied by 2 pi I, we have negative 8 pi I.
So you answered F, right?
Yes.
All right. Anybody else? Anybody else who answered B or C, because those were the most popular? All right. So yes, you're correct. So we said that this has residue as z equal to this z equal to 0 is z not equal to 0 is inside. So this is, you see, z is z minus 0. So residue at 0 is evaluated as limit of, let me write a limit as z approaches 0 of z times the function 4 minus 3z divided by z times z minus 1, and that becomes z cancels. That becomes 4 minus 3z divided by z minus 1 evaluated as z equal to 0. So if you put z equal to 0, this becomes 0, this becomes 0, this becomes negative 4. And the integral of fz dz becomes negative 4 times 2 pi I. So that becomes negative 8 pi I. All right?
So, Professor,
Yes.
why in the previous one was multiplied by c minus 1, and this is just multiplied by c,
Because
by z?
because z minus z naught is 0, is z minus 0, which is z.
Okay. But you're, okay, yeah, then you,
Z naught is 0, so z minus z naught becomes just z.
yeah, I got it.
All right. Thanks for asking the question. Any other questions? All right. So that becomes negative 4. Now, what if you have this one? What do you think? Let me launch the poll again. All right, half of the answers are in. This shouldn't take long. All right, so we're getting better. So I'm going to end that soon. If you want to answer, please answer faster. All right, this time the most popular answer is correct. So we're getting some improvement here. So we said that if you have several points, the integral of fz dz is equal to 2 pi I times sum of the residues. So becomes 2 pi I times negative 4 plus 1. We already calculated residue. 1 was negative 4 at z equals 0, and at 1 was 1. So it becomes 2 pi I times -3. So it becomes -6 pi I. All right, so I guess we're getting in now. Any questions? All right. So here is the same problem from the book. All right. Now we want to integrate tan of z divided by z squared minus 1 counterclockwise around the circle z equal to 3/2. Absolute value of z equal to 3/2 means that it is centered at the origin and it has a radius of 1.5. What do you think the answer is? This takes a while, so let me do it myself. Tan of z. At what points tan of z is non-analytic? Does anybody remember?
1 and -1.
Sorry?
Is that 1 and -1?
No, tan of 1.
Oh, 10, might have been.
10 is 0 and negative pi, or pi, right?
The tan of z is, just remember, tan of
0 and
z
pi.
is
Oh,
sine z over cosine z.
so
And
then it would be I and negative I. Or,
Pi over 2.
yes, pi over 2 negative.
uh,
The odd numbers of pi over 2, right? When z is odd numbers of pi over 2 means plus minus pi over 2 and plus minus 3 pi over 2 and plus minus 5 pi over 2 and so forth, right? At these points is non-analytic. But how much is pi over 2?
It's 1.57, so it's out.
It is outside, right? All of these are outside the circle. So tan of z is analytic inside and on the circle. So tan of z is not an issue. It's an analytic function. All right. So the only problem is with z squared minus 1 that's in the denominator. And so z squared minus 1, as you mentioned, is z minus 1 times z plus 1, right? And these are two, if you set that equal to 0, you get z equal to 1 and z equal to 2. Sorry, -1. All right. So there are two residues here. We have to calculate two residues. Residue at 1 and residue at -1 of this function. And then once we have that, we add the two residues and multiply by the 2 pi I, and we get the answer. Okay.
So yeah, I got the answer is 0, right?
Answer is 0.
Yeah, because I feel like the two residue is like equal and opposite sides, so add them together we got 0.
No, you have to be careful. You're just saying that without calculation. You need to calculate. You don't guess or you don't go too fast. All right, let's find the residue of tan of z over z squared minus 1 at z equal to 1 first. So we said we can do two things. We can multiply by z minus 1 because z naught is 1 now. We can multiply by z minus 1 and then evaluate at z equal to 1, right? Or we can do the derivative with derivative of denominator. But I think at z equal to 1, calculating is better. Limit of z minus 1 of tan of times tan of z over z minus 1 times z plus 1 as z goes to 1. That this cancels out, so it becomes tan of z over z plus 1 evaluated at z equal to 1. So how do you count? What is the result here? I need to put z equal to 1. What is tan of 1? That's 1 radian. It has some value, right? So tan 1 divided by 2. So this is the residue at 1. What is the residue at z equal to -1 of tan of z divided by z squared minus 1? Becomes limit as z goes to -1, z minus -1, which is +1, times tan of z over z minus 1 times z plus 1. Right? And then now z plus 1 cancels. So you get a tan of z over z minus 1 evaluated at z equal to -1. If you put -1, becomes -2 in the denominator, but tan of -1 becomes also negative tan of 1, right? So tan of -1 divided by -2, but tan is a odd function. So tan of -1 is negative tan of 1. So it becomes again tan of 1 over 2. So the two residues are the same. If you add them, it becomes just tan of 1. So integral over this circle C of tan of z over z squared minus 1 dz becomes 2 pi I times sum of the residues, which is 2 pi I times tan of 1, because 1/2 and 1/2 becomes 1. So it becomes 2 pi I times tan of 1. And tan of 1 times tan of 1 is about 1.5. So this will be closest to this answer. Of course, this is not exactly 3 pi I, but very close to 3 pi I. Okay. Does it make sense? Any questions? So this
Yeah,
is,
why did the tan of 1 over 2, why isn't it tan of 1 over 2 again?
which one? The second line or third line?
The third line, when we plugged in the residue, it becomes 2 pi I over tan of 1. And why isn't it tan of 1 over 2?
Because there are two of them, right? Is tan of 1
Oh.
divided by 2 plus tan of 1 divided by 2.
Right.
Sum of the
Okay.
residues, right?
I get it now. Thank you.
You're welcome. All right. Any more questions? All right. So
And that tangent should be in radians, right?
that's right. It should be in radians. Yeah. Yeah. Make sure when you want to calculate that, you put your calculator in radian mode. All right. So this is the type solution. Tan of z over z squared minus 1 is 2 pi I times residue of that at z equal to 1 plus residue at z equal to -1. The residue at 1 becomes tan of z over 2z. Here you see the book use the second formula, which is the derivative of the denominator, which is 2z, and then evaluate at z equal to 1, and again evaluate at z equal to -1. So becomes tan of 1 divided by 2 plus tan of -1 divided by -2. Those are the same. So it becomes 2 pi I times tan of 1, which is 9.7855, which is about close to 3 pi I. All right. Tan of 1 is close to 1.5. Any questions? This is another example. When we have essential singularity. So here we don't have essential singularity. You see pole of some order. This one is a analytic function, but the denominator you can write, you can factor. It becomes some poles, right? But this one, e to the pi over z, has essential singularities because when you expand it in terms of z, it has infinite powers of negative z. I mean, it's infinite negative powers of z. So, all right. And c is the ellipse, and 9x squared plus y squared equal to 9. So you can divide this by 9. You say x squared over 1 plus y squared over 3 squared equal to 1. So you see that this is extended in the y direction to 3 and negative 3, and extended in the x direction to 1 and negative 1. So the path is like this. It says ellipse like this. So here it is 3 times more height than the width. Okay, is 1, negative 1, negative 3, and 3, right? This is the path of integration. And now we want to see, okay, how many, for this can be split into 2 integrals. The first integral has some poles. The second integral, to find the residue, we don't have a formula for it, because you see those formulas are all for non-essential singularities, means that there is a pole of some order m. But e to the pi over z doesn't have a pole of m order. It has non-essential singularity, essential singularity. Okay, so we need to separate that. So to find the first part, integral of z e to the pi z over z to the 4th minus 16 dz, we need to find its poles, where the poles are, and we find the residues at the poles that are inside that ellipse, which is path of integration, C. All right. So the numerator, as I said, is analytic. The denominator, we can write z to the 4th minus 16 is z squared minus 4 times z squared plus 4. And z squared minus 4 can be written as z minus 2 times z plus 2. And z squared plus 4 can be written as what? Z minus 2i times z plus 2i, right? So it has poles at 2 and negative 2 and 2i and negative 2i. You see, negative 2 is here, 2 is here, right? So these are outside, but 2i and negative 2i are inside. So z equal to 2i and z equal to negative 2i are inside C. All right. So we need to calculate the residue at these 2 points. So what is the residue of z e to the pi z divided by z to the 4th minus 16 at z equal to 2i? We can use the P over Q formula. We calculate the derivative of the denominator. That's easier. So it becomes z e to the pi z divided by 4z cubed, evaluated at z equal to 2i, right? And if you put 2i, what do we get? Becomes 2i e to the 2 pi I, right? and divide by 4 times 2 pi 2i, sorry, 2i cubed. How much is that? What is e to the 2 pi I?
1. So I got -1/16.
Yeah. So you see, I squared becomes -1. I cubed is I. Negative I cancels with that I. And we have 3 powers of 2. One of them cancels, or can cancel one of these with one of these. So I squared becomes 1. 2 squared becomes 4. 4 times 4, 16. E to the 2 pi I is also 1. So it becomes 1/16. Negative, sorry. -1/16. All right. So this is one residue. What is the residue of z e to the pi z over z to the 4th minus 16 at z equal to -2i? Again, that becomes the z e to the pi z divided by 4z cubed evaluated at z equal to -2i. So that becomes -2i e to the -2 pi I, or 2i pi, divided by 4 times -2i. I can cancel one of the z's from the beginning. -2i cubed, and this cancels with one of these. So you get -2 squared, I squared, right? And e to the -2 pi I is also 1. So you get, this is squared. So it becomes, again, negative, because I squared becomes -1/16 again. All right. So this is the two residues of the first one. So the integral of the first one becomes the integral over c of z e to the pi z divided by z to the 4th minus 16 dz becomes 2 pi I times -1/16 minus 1/16. So that's -1/8 times 2 becomes -pi I over 4, right? So this is the first integral. The second integral, there's no formula for the residue. We have to do expansion. So what is z times e to the pi z, pi over z? Pi over z. Okay. We can write z times this e to the pi z, pi over z, in Taylor expansion becomes sum of pi over z to the n divided by n factorial, right? So that means it's z times 1 plus pi over z plus pi squared over z squared, or 2z squared, plus pi cubed over 3 factorial z cubed and so forth, right? And if you multiply by z, you get z plus pi squared over 2z plus the rest of the terms that have, the next one will be pi cubed over 3, pi cubed over 6 z squared, and so forth, right? So what is B1? B1 is the factor of z minus z naught. And this has a pole at this point, essential singularity at z equal to 0, because we have all these powers of 1 over z, or negative powers of z minus 0, right? So we look at the first one, this has z 1 over z minus 0 to the power 1. So that's this one. And the coefficient of that is pi squared over 2. So B1 is equal to pi squared over 2. And that is the residue. So this second integral becomes 2 pi I times pi squared over 2. So if I can write, I don't have room here. Let me make room here. Integral of z e to the pi over z dz becomes 2 pi I times pi squared over 2. So becomes pi cubed. So I pi cubed, right? So the first one is this. The second one is pi I pi cubed, and then you add the two together, right? You can factor I pi, then becomes times pi squared minus 1/4. So the total integral becomes I pi I times pi squared minus 1/4. All right?
Professor, I have one question.
Yes, please.
I don't know how to put it, but for the second integral, actually you said there is no integral for the second part, right? For the CE to the pi over 2.
ZE to the pi over z. Yes.
Right, yeah.
It has essential singularity, okay, because you have all the negative powers of z, and it has essential singularity at z equal to 0. All right?
Right.
The formula that we have for residue is for poles of nth order, not for essential singularity.
Oh, so that's where we know. Okay, thank you, Professor.
In that case, when we have essential singularity, we have to write down the Loren series and find out what B1 is. And
Right.
that's what we did.
Okay, thank you, Professor.
You're welcome. Any other questions? All right. So these are good examples. These are from the book. So the book solution is this: since z to the 4th minus 16 equal to 0, add plus minus 2i and plus minus 2. The first term of the integrand has simple poles at plus minus I inside C, with residues given this way: negative 1 over 16 and negative 1 over 16. The second term of the integrand has an essential singularity at 0 with residue pi squared over 2 as obtained from this. So z plus pi squared over 2 times 1 over z and so forth. So answer is 2 pi I negative 1 over 16, negative 1 over 16 plus 1/2 pi squared, and then you can write it as pi times pi squared minus 1/4 I, which is 30.221 I. Okay? That makes sense? Any questions? All right. Now, we want to apply the residue integration of real integrals. We want to apply to real integrals. There are some real integrals that we cannot evaluate in real calculus. So residue integration can also be used to evaluate certain classes of complicated real integrals. This shows an advantage of complex analysis over real analysis or calculus. Integrals of some rational functions of cosine theta and sine theta. There are different classes of integrations that we can do using integral in residue theorem. Suppose we have this kind of integral from 0 to 2 pi, any function of cosine theta and sine theta d theta. So the integral is over theta from 0 to 2 pi. Now we can apply residue theorem to and do this kind of integral. We set e to the I theta equal to z. And then we get cosine theta, which is 1/2 of e to the I theta plus e to the negative I theta. So it's e to the I theta becomes z, e to the negative I theta becomes 1 over z. So cosine theta becomes 1/2 of z plus 1 over z, all right? And sine theta is 1 over 2i e to the I theta minus e to the negative I theta. So it becomes 1 over 2i z minus 1 over z. So this means that if we take this change of variable, we can write cosine theta and sine theta in terms of z. Okay, so then we can write any function of sine and cosine in terms of z. So it becomes a function of z only. And then dz, dz over d theta from here, if you take derivative with respect to theta on both sides, become I e to the I theta. Again, e to the I theta is z. Therefore, d theta becomes dz over iz. You see that? Dz over d theta becomes iz. Therefore, d theta becomes dz over d theta. Iz d theta becomes dz. Therefore, d theta becomes dz over iz. Right? So we have d theta also here. So we can change the variable entirely to z. So the integral becomes f of z, some function of z, because we replace all sines and cosines in terms of z. And then for d theta, we have dz over iz. And then z goes over the unit circle. So z equal to I theta ranges counterclockwise once around the unit circle, absolute value of z equal to 1. Then we can write this as 2 pi I times the residue, sum of the residues inside the unit circle. Right, so we can calculate all the residues of this function that is here now, and then see which one of the poles are inside. We find all the poles, and the ones that are inside the unit circle, we find residues of those and multiply 2 pi I, we get this integral. Okay, but sometimes these integrals are not easy to do in real function, in real calculus. All right. Any questions? All right. A simple idea, right? So change of variable. This is an example. Integral from 0 to 2 pi d theta divided by square root of 2 minus cosine theta. You see here, square root of 2 minus cosine theta is, in the denominator. This is not an easy equation, easy integral to do. All right. So let's see what happens if we apply this method. We use cosine theta equal to 1/2 z plus 1 over z, and d theta equal to dz over iz. Then the integral becomes like this. Instead of d theta, we put dz over iz, and then square root of 2 minus 1/2 of z plus 1 over z. And then we can write it like that. We multiply this iz in the denominator. So we have, let's see how this came about. If you multiply by iz, I is here. So we have square root of 2 times z minus 1/2 z squared minus 1/2, right? If you multiply by z and I, so I we can keep here. So you get the square root of 2z minus 1/2 z squared. Z becomes z squared because multiplying by z, and then 1/z becomes just 1. So you have negative 1/2, and then you can factor 1/2, factor negative 1/2, make negative I over 2. Then this this becomes z squared, and this becomes a negative 2 square root of z. Sorry, negative 2 square root of 2 times z, and the other one becomes plus 1. And then we can factor this. Factoring by 2 numbers. Actually, this is like you can just do z. If you set that equal to 0, you can see that the solutions are z equal to negative b, negative, or becomes plus 2 square root of 2 plus minus square root of excuse me, square root of b squared minus 4ac. B squared becomes 4 times 2. That's 8. Minus 4 times 1 times 1 minus 4. So it becomes square root of 4, which is 2. Divide by 2. So it becomes square root of 2 plus 1 and square root of 2 minus 1, right? So this can be written as negative I over 2 times z minus square root of 2 minus 1 times z minus square root of 2 plus 1. Okay? So, and which one of these are in the unit circle? The square root of 2 plus 1 is not in the unit circle. This one is inside the unit circle. Right? So if this is inside the unit circle, we need to calculate the residue of this for this integral inside the unit circle. I mean, at this point, sorry. All right. So we do residue of 1 over this expression, z minus square root of 2 minus 1 times z minus square root of 2 plus 1 at z equal to square root of 2 minus 1. So it means that we have to multiply limit as z goes to square root of 2 minus 1 this function times the square root of z minus z naught, which is square root of 2 plus 1 divide by z minus square root of 2 minus 1 times z minus square root of 2 plus 1, and this cancels out, so it becomes 1 over z minus square root of 2 minus 1 evaluated at z equal to square root of 2 minus 1, right? And then that becomes 1 over square root of 2 minus 1 minus square root of 2 minus 1, right? Square root of 2 cancels, you get negative 1/2. All right. And if you have negative 1/2, we have a factor of negative negative I over 2. So this becomes 2 pi I, and we have a factor of 1 over negative I over 2 times this negative 1/2. right? So this is -1/2 with -1/2 cancels out. I with I cancels out, you get 2 pi. All right. Any questions?
For the square root of 2 plus 1, it is outside the circle because its value is greater than 1, or?
That's right. Square root
Okay.
of 2 plus 1 becomes 2.141, right? 2.42, and the square root of 2 minus 1 becomes just 0.42, right? So that's inside, that's outside. Right. All right. So only the residue of those that are inside the unit circle matters. The other ones don't matter. Okay.
Yeah,
This is,
thank you.
This is also as long as we don't have any residue, any singular point on the unit circle. If we have the units residue on the unit circle, at this point, we don't know how to deal with it, but later on, we're going to address that, okay? So here, so far, we're talking about the singular points that are inside the unit circle. If they are on the unit circle, then we need to deal with it another way, okay? Any more questions? All right, so this is the thing. Simple code adds 2 equal to the square root of 2 minus 1, where inside C with residue given by that -1/2. So the answer is 2 pi I times -2 over I. This is this factor is brought up and flipped over, right? So we have -2 over I times -1/2, and -1/2 and -2 cancels. I with I cancels, you get 2 pi, right? All right, so this is the way the book did it. All right. Another large class is integral of fx dx from -infinity to infinity. So there are some functions whose integral from -infinity to infinity over x is not easy to calculate. Such an integral whose interval of integration is not finite is called an improper integral. And they are defined like this. Integral from -infinity to infinity fx dx is equal to limit of integral from a to 0 fx dx as a goes to -infinity plus the limit of integral from 0 to b fx dx as b goes to infinity. So we make it instead of going negative to infinity to infinity, from -infinity to infinity, we go from from a to b, and then we send this to -infinity, and then send this to +infinity. Okay, this is the way the integrals are defined. The improper integrals are defined. If both limits exist, we say that this integral exists, and it will be the same as sum of these two limits. We may couple the two independent passages to -infinity and +infinity. So say that you get a and b, we can say like b to -b, or -a to a, or -r to r. So if you do that, you can say this integral can be written as limit of -r to r fx dx as r goes to infinity. This has an advantage. It's called Cauchy's principal value. Cauchy principal value of an integral. It may exist even the limits in 5, means that this equation doesn't exist. Example is this: limit of -r to r x dx as r goes to infinity becomes limit of r squared over 2 minus r squared over 2 equal to 2. But you see that each one of them from 0 to b doesn't, as b goes to infinity, doesn't exist. Limit of x dx from 0 to b as b goes to infinity doesn't exist. It becomes infinite. So sometimes this is even better than these two. All right. So this is called Cauchy's principal value, and that is what we use in order to calculate this integral. All right. So let's see what we can do with this. We assume that the function f of x in this equation is a real rational function whose denominator is different from 0 for all real x. So that is a limiting condition that, you know, doesn't have to, it shouldn't have any zeros on the real x. But we will take care of that later. And f of z in the denominator has a degree at least 2 units higher than the degree of the numerator. And of course, if it is not the case, the integral doesn't exist. If the denominator is not higher than the degree of the denominator is not higher than the degree of the numerator by 2, the integral becomes infinite. So we consider the corresponding contour integral. So instead of saying this integral, we talk about this integral over contour C. Contour C goes from negative r to r on the x-axis and then goes on a circle from r to negative r. We call it S. All right. So if we look at this around this closed path C that has one piece straight from negative r to r, the other piece is on a semicircle from r to negative r, then we can split this integral into 2 pieces. All right. And then f of z has finitely many poles in the upper half plane, because you see this, you find the poles of this. It has some, it is rational function, right? It has some poles. Some of them are above the x-axis, some of them are below the x-axis, and they have finitely many poles because the denominator is a polynomial. It is not an infinite, it's not a transcendental function. So if we choose r large enough, then C encloses all the poles, and integral of fz dz over C equals integral of fz dz over S plus integral from negative r to r of fx dx. All right. And then if you make r go to infinity, this part, because f of z goes to 0 over this circle, because the denominator is larger by a power of 2 at least, and the integral becomes 0. This integral becomes 0 because of this condition that the denominator is of degree at least 2 units higher than the numerator. And because you take the integral, this circle, the size of this circle goes to infinity by 2 pi r, but the function goes to 0 by 1 over r squared. So that goes to 0, right? So this integral becomes just this real integral. Does it make sense? And then we can write this with the residue theorem equal to 2 pi I times sum of the residues on upper half plane. The residues that are up here, not the ones that are down here. All right. So this is the way we can evaluate this kind of integral. So we say integral of negative infinity to infinity of fx dx is equal to 2 pi I times sum of the residues of f of z on the upper half plane. Make sense? So this is a formula now. You don't need to have, you don't need to do all of these. So if you have a function f of x dx that doesn't have any poles, it doesn't have any zeros on the x-axis, and then the integral from negative infinity to infinity of fx dx becomes 2 pi I times sum of the residues of f of z. You see, this is f of x here. Here we have f of z. So we look at it as a complex function and find its residues and see which ones are, find the poles and which ones are above the x-axis and find residues above at those points and multiply by 2 pi I, sum of the residues times 2 pi I. All right. So this gives us that integral, the real integral. Any questions? This is an example. So what is integral from 0 to infinity of x dx over 1 plus x to the 4th? This is an integral that cannot be done in real calculus. Okay. And the degree of the denominator is 4. The degree of numerator is 1. So it satisfies the condition. It has 4 simple poles. So 1 plus z to the 4th can be written as z squared minus I times z squared plus I, right? And then if z squared minus I is 0, if z squared is equal to I, we can write this as e to the I pi over 2. So z becomes e to the I pi over 4, right? And of course, this can be also plus or minus. This can be equal to plus or minus, right? So, and if z squared is equal to negative I, let me see, negative pi over 4.
I think
No,
on the top right there is z equal plus and minus I pi over 4. Plus
sorry?
before I, yeah, before e, yeah.
Yeah. So z squared equals to I, and yeah, there are two. There are two of them, right? Remember? There are two solutions to z squared equal to I. Is e to the I pi over 2 and e to the I 3 pi pi over 2 plus pi. So 3 pi over 2. No, 5 pi over 2. Because you can do.
No, I mean that can be e to the I pi over 4 and minus e to the I pi over 4.
Oh, yeah. Yes. Yeah, I wrote that here. But why e to the negative? Oh, yes. But then e to the negative pi over 4, if you square that, becomes e to the negative pi over 2, which is negative I. That is not the case. This z becomes e to the pi over 4, or e to the I 5 pi over 4. If you square this one now, it becomes 10 pi over 4. 10 pi over 4 is 2 pi plus pi over 2, right?
Professor, I mean e to the I pi over 4 and negative e to I pi over 4. So
No. That you see here, e to the I pi over 4 is this. E to the negative pi over 4 is this. And if you square this one, if this is z, z squared will be I, because the angle doubles, right? But if you square this one, this is z1, this is z1 squared. This is z2, then z2 squared becomes negative I, doesn't become I. So if z squared is I, one of the answers is this, the other answer is this. Because this, if you double this angle, it comes back here. Yeah, negative, yeah. Plus minus. Yeah, that becomes plus minus. Good job. We can say plus minus this, which is this one and that one. Yeah. Becomes this one and this one. This is the Z1. It can be either this or that. And for the other one, Z squared equal to I, Z squared equal to I, negative I, sorry. One of the answers is this, the other one is this one. So we have 4 roots in here. So we have 2 of them above the x-axis, 2 of them below x-axis. So Z1, Z2, this, let's call this Z3 and Z4. These are the poles of this function, right? Or this function. So what is that? Z1 is e to the I pi over 4, and this one becomes e to the I 3 pi over 4. All right. So we need to calculate the residues at these 2 points. So what is the residue of 1 over 1 plus z to the 4th at z equal to e to the I pi over 4. Remember, this is like a rational function. We can do it's p over q. We can do p at z naught divided by q prime at z naught. So it becomes 1 over 4 z cubed evaluated at z equal to e to the I pi over 4. So if you do that, it becomes 1 over 4 e to the 3I pi over 4, which is e to the negative 3I pi over 4 divided by 4. All right. And residue of the same thing at z equal to e to the 3I pi over 4 becomes 1 over 4z cubed evaluated at z equal to e to the 3I pi over 4. And that becomes 1 over 4 e to the 9I pi over 4. But you see, 9 becomes 8 plus 1. 8 times I pi over 4 becomes 2 pi I, that you can ignore. So it becomes like pi over 4, and becomes e to the I pi over 4 divided by 4. All right. So it becomes 1/3 of this and 1/3 of that. All right, so these are the residues. Let's see. So we have e to the I pi over 4, e to the 3 pi I over 4, e to the -3 I pi over 4, and e to the -pi I over 4. So these are the 4 points. The first two lie in the upper half plane. So this becomes that 1/4 of e to the -3 pi I over 4, which is -1/4 of e to the pi I over 4. And the other one becomes e to the -9, again, the same as e to the I pi over 4. So one is negative, one is positive. All right, so, and then if you add them, you get e to the I pi over 4 minus e to the -I pi over 4. So that becomes sine of pi over 4 times 2i. So 2i sine of pi over 4, and 2 become these 2 and 2 cancel with this, I and I cancel with that, and again becomes pi sine of pi over 4. So pi sine pi over 4, and sine pi over 4 is square root of 2 over 2, or 1 over square root of 2, so it becomes pi square over square root of 2. So this is integral from -infinity to infinity, but we wanted from 0 to infinity. But this function is an even function. So the integral from 0 to infinity is half of from -infinity to infinity. So the answer will be from 0 to infinity, dx over 1 plus x to the 4th becomes pi over 2 square root of 2. All right. All right. Any questions? All right, we stop here. Well, then we continue next time with the Fourier integrals.